This example, we want to talk about the graph node coloring problem. So consider this graph. It has a number of nodes that are connected to each other, and from the graph we just know how the nodes are connected to each other, that this is the input data of the problem. Okay, so the question is, if we want to color the nodes in a way that no two adjacent nodes are painted with the same color, how many colors do we need? What is the minimum number of colors that we need? So suppose if we have n nodes in our graph, then if we have n colors, we can easily solve this problem. Okay, but there is a much smarter way to do this. For example, if you look at this graph, you can see by only two colors the nodes are painted in a way that no two adjacent nodes are colored with the same color. So if you look at here, these two have different colors, but this yellow and this yellow one have the same color, but because they are not directly connected to each other, that's fine. So how can we formulate it as an optimization problem? So first of all, we need the input data of the graph. So Lij is 1 if I is connected to j, and xic is telling us node I is colored with the color C. So we have a set C, it has a range of colors, and I is the set of nodes. So we want to find out an optimal mapping between nodes and the colors. So we want to know which node should take which color. Okay, so xic is a binary variable, xjc is the binary variable, I and j are alias with each other, so they are from the same sets, nodes. Summation of these two variables multiplied by Lij less than 1. So if Lij is 0, it means that the constraint can be easily satisfied because 0 is less than 1, it's automatically satisfied, it's inactive. And if Lij is 1, then xic plus xjc less than 1. So that constraint is defined over the sets I, j, and c. For every I and j and c, if Lij is 1, then the summation of these two variables should be 1. It means that if two nodes are connected to each other, they cannot get the same color. Okay, and y is the objective function, should be bigger than or equal to cxic for every I and c. And the last constraint is telling us that every node should take only one color. So every node, every color can be assigned to only one node. Okay, so let's have a look at the Python code for this purpose. So the Python code is here. I import required packages. So first of all, matplotlib networks for drawing the graph kind of plots. This is a built-in kind of facility in the networks package to plot the graphs with the given sizes, and also the position of these nodes are determined. And then we will import the Pyomo, matplotlib, numpy, random, and also panda. Okay, and then we construct the model. We assume that the model is an abstract one. N is the number of nodes, I is the set of nodes, j is the same, color is set of colors, the maximum number of colors will be this number of nodes, and L is a parameter showing that if I is connected to j actually, and x and y are some variables. So x is a binary variable, but y is a non-negative reals. So we can easily solve that. Let's write down the equation that we need. So you can see here that L multiplied by xic plus xjc less than 1. That constraint is defined over I, j, and color, and that rule should be followed. And then the objective function should be bigger than c multiplied by model xic and that constraint is defined over I and C, you can see here. And finally, every node should take only one color. That's here, and the objective function is model.y. And the sense is minimization, so we want to find out the minimum number of color required for painting that graph. So since the model is linear, I choose the GLPK solver, and here we have already created the graph, you can see, and also here we have access to the number of nodes in that graph. So model.n is initialized somehow, and then the instance will be created here. Okay, so let's run the code so far to see what's going on. So I run the whole tabs and I will explain the results. So let's begin from the first tab. So the first tab, the required packages are imported, this second one as well, and the model is created here. It is the instance will be constructed. It means that the L and other constraints are fed into the model, but keep in mind that I have not specified the L yet, so the connectivity matrix is not specified yet. So I have initialized that it's equal to 0, so all of them are not connected to each other, but the model is right there, and we have to update the L and feed the right connection matrix to the instance. So for this purpose, what we do is we can easily find out which nodes are connected to which. So for we create a for loop edge in g.edges. If these two are connected to each other, then instance.lij is equal to 1. Okay, so from nodes, and two nodes are found using these commands. Okay, so, and then what we should do next is let me double check it here. So instance is updated, and L in the instance is updated, and we have already defined it as a mutable parameter. You can see it here, it's a mutable one, so it means that you can update their quantities. And then we can ask the Pyomo to solve it for us. So it is trying to solve the problem. Since it has some binary variables inside the model, it may take time to solve that. And so the model is solved. Okay, you can see that L is printed here, for example. It's not really necessary to print all these, but for checking purpose you can do it. So it means that 1 is connected to 2 and the value has 1, and so on and so on. Okay, and finally you can see here that the graph is colored. Okay, and each XIC has taken the value. So let me show you what's happening here. So here we can see easily that what are the values of XIC. For example, node 1 color 1 is 1. It means that node 1 is colored with color number 1. Node 2 is colored with number 2. Node 3 is colored with the number 1. Node 4 is colored with number 2, and so on and so on. Okay, so and already we had specified each number means which color. Okay, so we should have a list for the columns, and we can choose which color is selected. Okay, and that's it.